Okay, so now let's talk about flat manifolds in the context of what we learned about curvature tensors. So, um, so basically, it's like, if you recall, if the Riemann-Christoffel curvature tensor vanishes, then what it means is that parallel transport with respect to the affine connection is path independent, right? Okay, all right. So let's try to use this idea then to introduce an affine coordinate system on the manifold, at least locally, right? So, so we're going to pick some base point that's like in the manifold, and we're going to introduce some coordinates on the tangent space. So let's consider a set of basis vectors. Let's denote this by EI, right? Which are in the tangent space at a point. Right. So once you have that, and you have, it's like a affine connection, we can talk about, constructing geodesics, which are in those directions, right? So we can construct geodesics which pass through that point. We can construct actually n geodesics which pass through that point. In the direction E sub I. So in each of the each of the basis vectors, right, you want a geodesic which goes in that basis vector direction. Okay, so the claim is that when you do this, it's like this is going to generate n coordinate curves. So this will generate n coordinate curves. Theta I with the same sort of tangent vectors sort of EI everywhere. Right. And the idea that is that you can, as you move along this, it's like, it doesn't matter, right? Because in essence, if it's path independent, more or less, it's like what that means is that, the coordinates you introduce, it's like, it doesn't matter how you choose to move. It's like in the geodesic directions, you could move first in the first direction and in the second direction versus moving in the second direction. In the first direction, you'll get to the same point. It's like because of this sort of vanishing curvature condition. Okay. So since the tangent vectors all in parallel. Okay, well, the tangent vector is to the coordinates occurs. Eta I are all parallel. What that means is that the directional covariant, or the covariant derivative of Ej Ei equals to 0. Well, actually, technically, it's it has this Kronecker delta property, right? And then from this implies that the connection coefficients vanish. And so basically what happens then is that, and if you recall, it's like if the connection coefficients vanish, it's like then what basically happens is that, you don't have to evoke this more sophisticated notion of a covariant derivative. The usual notion of derivatives work. So that basically means is that this coordinate system which you have, it's like on the manifold, which is obtained by looking at geodesics, right? That gives you an affine coordinate system consisting of geodesics. So, and that this manifold is flat, right? So this gives an affine coordinate system on this flat manifold, which consists, and the coordinate system consists of geodesics, or the coordinate curves consists of geodesics. Okay. And the connection coefficients vanish at any point. Everywhere. Okay. All right. So again, it's like this notion of this Riemann-Christoffel. It's like curvature is helpful because it helps you characterize spaces. It's like which are flat, right? So if the Riemann-Christoffel curvature tensor vanishes identically, then the space is flat. Okay. All right. Let me stop here.